as Stephen mentioned, you'll be able to, you can see that outside and be able to tour that here in a little bit. So the goal of this presentation is to give you some idea of how we define radar scans for different meteorological phenomena and learn some of the advantages and the disadvantages for using these. As well as I'll talk briefly about some of the radar system parameters that we configure so that you have some idea of what the best options are there as well. And then we'll do a couple of quick examples too, so you can apply your knowledge to some real life scenarios. And so a little bit of terminology before we jump in. First, the radar beam is the volume that the transmitted signal is passing through. So the radar beam goes out, it scatters off of some target, and some of that energy comes back to the radar. And so one of the most important quantities is looking in range. So this is the path that the radar beam is going to go along. And then the azimuth angle is the direction that the radar scans around horizontally. And then the elevation is the angle relative to the ground, moving up in the vertical direction. So the elevation angle is essentially your inclination above the horizon. Another important area of terminology is the radar range gate. So each of these little pixels on here is a radar range gate. So the radar divides up based on the length of a pulse, divides up the data along the transmitted signal into individual gates. So the spatial resolution along the ray is defined as our gate spacing. So common values like between 30 meters and 250 meters, depending on the length of the pulse. And there's also the pulse period. This is the time between two pulses that the radar transmits. It's usually about 1 millisecond. So commonly the radar transmits
already there. Okay.
1,000 pulses per second. So when we're designing a field experiment, there's several things that we need to consider before we set up our radar scans. And fundamental to this is, first of all, is the temporal resolution. So how quickly do we need to make observations? And this will depend on how fast the phenomena that we're looking at is evolving. So for example, a tornado could form in just 1 or 2 minutes. So it's a pretty fast evolving phenomena. And if you really want to see how the tornado forms, you don't just want to see it wasn't there and then suddenly it is there 1 to 2 minutes later. You want to sample that pretty finely in time. So you need to see about 5 to 10 time samples to really get a good idea of what processes are occurring. So this would require about 10 to 20 second time sampling for a tornado to see its formation. Similarly, when you just look at thunderstorm initiation, this occurs over a period of about 10 to 20 minutes. So if you want to attend 5 to 10 samples, you need about 1 to 2 minute temporal sampling to adequately see the evolution of the clouds and the development of precipitation. So next, we need to consider how high up we want to scan. So the radar has a finite amount of time to scan. So the smaller the area you scan, the faster you're able to scan it. So the height and temporal resolution kind of go hand in hand as a trade-off. So for a sea breeze circulation, for example, this tends to be 1 to 2 kilometers deep. You have relatively cold air close to the surface, and then you may have some, for example, Kelvin-Helmholtz waves at the interface between the cool and the warm air. So to sample this, you need to be able to scan about 1 to 2 kilometers deep. In contrast to that, a thunderstorm that's initiated by the sea breeze could be much deeper. So that would go maybe 12 to 18 kilometers that you would be desiring to scan. So next is your vertical sampling. So with the radar, you typically have a certain amount of time you want to scan, and that's going to dictate how many different slices of the atmosphere you can make during that time. So our vertical sampling is how many of these vertical slices we want to make through this vertical column that we're sampling. So for example, if a thunderstorm's 18 kilometers tall and we want to get 1 kilometer sampling, we would make measurements over 18 different elevation angles. But if we want to double our vertical resolution, to 500 meters, we need to make 36 elevation angles. So that's going to take quite a bit more time than it would otherwise. And then finally, the spatial resolution is impacted by the radar's range, or the range of the observations. So if we're looking at a storm that's really close, we have better resolution. And this is because the radar beam broadens in range, so it gets wider as you go farther away from the radar. So as you go to farther range, the cross-beam resolution gets worse. So for example, at 10 kilometers in range, Raxpole's resolution is about 175 meters. And then at 50 kilometers in range, it's 875 meters. So it's quite a bit worse. You're getting close to a kilometer when you get to 50, 60 kilometers in range. The range resolution is controlled by the radar hardware, so it's the same for each gate. It's usually pretty easy to get really good range resolution. It's usually a lot harder to get good cross-beam resolution. So next, talk about some of the different scans that you can do with a weather radar. So the first one's called a planned position indicator, or PPI scan. And this is where the radar rotates around at a fixed elevation angle, and it completes a 360-degree scan about its vertical axis. So if you've looked at data from NEXRAD, you'd see PPI scans. This is what the NEXRAD radar commonly uses for weather surveillance. And the advantage is it gives you excellent horizontal coverage of your data. But oftentimes you'll have large gaps in vertical coverage because the PPI scans are done at angles where you have large gaps between them. And that's due to the scan time constraints. Here's an example of data from Raxpole during the ESCAPE project in Houston that we did this summer. These are a couple of thunderstorms. So you can see, you get a nice horizontal picture of the data from a PPI plot. So another type of scan is a range height indicator scan. And this is where the radar scans at a fixed azimuth angle. So it's going to go up and then down in elevation, rotating upward from the ground up to the maximum elevation of interest. So the RHI scan gives you really good vertical detail. So it covers all elevation angles. There's no gaps. And this is an example of an RHI scan. So you can see no gaps in your vertical data. But the big disadvantage of an RHI scan is you don't have any horizontal context to interpret it unless you do other PPI scans. So as you can see here, you get a nice vertical cross section through a thunderstorm as part of, or from the RHI scan. And finally, another type of scan is a sector scan. So similar to a PPI scan, you're scanning in a horizontal direction at a constant elevation angle, but you're doing a sector, so you're not scanning 360 degrees, you might be scanning 90 degrees. So the advantage of this is you can decrease your scan time because you're not covering as much area in azimuth, so the antenna doesn't take as long to scan this area as it does to make a full 360. But a disadvantage is that the area of interest needs to be pretty isolated. So you could miss other storms, or you could miss some of the environmental data that might be important for your study. So for Raxpole, why would you think that sector scans would be less useful? And I'll give you a hint. The Raxpole does 2-second PPI scans. So for Raxpole, the sector scan is less useful because it can already do 2-second PPI scans. So for the antenna to stop and start, it's going to take at least 2 seconds. So we generally don't do sector scans with Raxpole because it can already scan so quickly. So putting this all together, the way this is done is through using a volume coverage pattern. So a volume coverage pattern, or VCP, describes a sequence of radar scans that you plan out and you do throughout the volume scan. So this can be a combination of PPI scans, RHI scans, or sector scans over your volume of interest. So you can use these interchangeably. So you could have some PPI scans, some RHI scans in the same volume scan. And then the time it takes you to finish a VCP is called the volume scan time. So here's an example of VCP where you start scanning at lower elevation angles, and you go up to higher elevation angles above that. So for NEXRAD, there's a couple of, there are many different types of volume coverage patterns. I'm showing here 2 in particular. The first one is VCP 12, and this is a severe weather VCP that NEXRAD does. And you can see it prioritizes observations very close to the ground. The difference in elevation angle is about 0.5 degrees for many of these low-level scans. And then the elevation angles get wider as you go up higher in the storm. And it takes about 4.5 minutes to scan these 14 elevation angles. So in contrast, that the clear air observations that NEXRAD does in VCP 32 it only scans 5 elevation angles, but it takes 10 minutes to scan those. So the radar, in this case, rotates very, very slowly. And this is done to improve the data quality that you get with the weak echoes that are seen by collecting many more pulses than you would in the severe weather VCP. So one important consideration when designing your volume scan is the radar beam height. So this is an example of looking in range and kilometers, what the height above the radar level that you would see is. So even looking at 0.5 degrees, if you go far enough away from the radar, looking at 2 kilometers or looking at 200 kilometers away, you would be looking over 4 kilometers above the ground. So even at the lowest common elevation angle, if you scan a storm that's really far away, you're probably scanning it at mid-levels instead of the lower levels of the atmosphere. So this is one reason why we do field experiments with mobile radars. We can take the radar really close and we can really finely sample the low levels of the thunderstorm well. But the disadvantage of that is if you want to collect data really close, then if you want to see the top of the storm, you need to use some of these higher elevation angles too. So there's some trade-offs here in terms of the overall scan time that's required. So taking a look at this first, if we were making measurements at 25 kilometers in range and the sea breeze is 2 kilometers deep, what elevation angle would we need to scan up to? So here, if we're looking at we need to scan about 4 degrees at 25 kilometers in range. So for a sea breeze at pretty close range, you would want to you could primarily just sample some of the lowest elevation angles. So for the thunderstorm case, if we're scanning 13 kilometers, the elevation angle will need to be quite a bit higher. So we're going to need to be able to scan here to 13 degrees or 13 kilometers above ground level. So we need to be able to scan up to 30 degrees. So here we have to cover many more elevation angles in order to be able to observe the thunderstorm. So here's another example of a VCP. This is from the Escape field campaign. I was looking at thunderstorms near the Houston area. And you can see here the data as the radar scans up in elevation angle. So it's going up to higher and higher elevation angles. You can start to see the echoes get a little bit weaker. This is from successive PPI scans that are done over about a 2-minute period using the RAC spool. Here's another example. This is a sequence of RHI scans that were done, basically doing vertical cross sections through the storm at different azimuth angles. And these were distributed primarily through the updraft region of the thunderstorm, spaced about every 3 to 5 degrees in azimuth. So here, RHIs are being made about every 4 degrees, from 320 to 348 degrees. And you see the different cross sections that result from that, those different cuts through the storm. And overall, the goal in Escape to get good data on convection, the observations were made about every 2 minutes for the revisit time. That way, the storms hadn't undergone such significant evolution that it was really hard to interpret the data. The real goal is really to understand the evolution of the thunderstorms. All right, so now I'm going to give you a chance to think a little bit about what types of volume scans you would do for a sea breeze experiment. Here, first consider if you're just targeting the sea breeze, would you prefer PPI scans, RHI scans, sector scans? And then if your project was also going to add on studying the thunderstorm, how would you design your VCP and how would that change from just looking at the sea breeze? So go ahead and maybe discuss amongst yourself for a few minutes, and then Stephen, I don't know if you can kind of facilitate some of the responses.
The sea breeze isn't all that tall. Would you rather do this way a whole bunch, the PPI one, and go around, or would you rather do an RHI where you're going up and then over and up and over and up and over and up, knowing that it's not all that tall?
I would just spin around.
We got one vote for spinning around. How many people agree? That's the vast majority of the class. Any thoughts for up and down? Nobody wants to do an RHI, David.
Okay. So it kind of depends on what you want to do. So a PPI scan will give you great horizontal context. So if you want to understand with the sea breeze, what maybe the differences are in the structure horizontally, or if you're trying to detect where shallow clouds are developing on the sea breeze and where precipitation is developing, the PPI scans can be very useful. An RHI scan, let's say you wanted to look at some of these wave-like structures on the top. It's going to be really hard to get the vertical detail and the continuity of data from a PPI scan. So that would be a case where the RHI scans can be really helpful for looking at some of the structure here, as well as maybe the convergence along the sea breeze. So now let's go to studying the thunderstorm. So let's say now you want to look at the thunderstorms that are going to form on the sea breeze. How would your VCP change? Would you change to PPIs? Or would you change to RHI scans? Would you do sector scans? Or would you stick with PPI scans?
All right, so the thunderstorm is really tall. Remember, with the mobile radar, you want to be really close. So are we still going around, or are we going up?
RHI.
We like up a lot better now.
Okay. So a big advantage of the RHI scan, if we're scanning up and down, is we're going to see that vertical structure really well. So the main disadvantage, let's say we are looking at a downburst that's occurring in the thunderstorm. If we slice that downburst perfectly up down the middle, we might be able to follow its evolution really well. If it's moving along and it moves outside our RHI scan, or we're trying to really understand the horizontal extent of it, then we might need to interweave some PPI scans to be able to understand that. The same thing if we were trying to see different thunderstorms and maybe compare how different thunderstorms are behaving in the same environment, a PPI scan could be useful there. But the RHI scan will provide a lot of very useful detail. Okay, so I just briefly want to cover some of the radar parameters. So the pulse repetition frequency is how many pulses per second the radar transmits. And this is important because it determines how far out the radar can see in range unambiguously. And then it also determines what the maximum velocity we can measure. So the maximum velocity, the higher the PRF, or the faster we transmit pulses, the higher the velocity we can sample. But the faster we transmit pulses, the shorter the range we can measure out to is. And you can see that here. These are some of the Raxpool's PRFs. So if you go to a high PRF, you can only see out to maybe 37 kilometers, but you get great velocity velocity range. So you can basically observe any velocities you might see in a sea breeze thunderstorm. Whereas if you try to see out really far, your velocity range of 7 meters per second might not even capture winds well that are common in a typical wind profile, even in a relatively low shear environment. So when we set these parameters, the most basic way to try and do this first is for your maximum unambiguous range, you'd like to set it for the farthest storm of interest and set your range to be beyond that storm. So the only problem is if we don't set it far enough, if there are other storms on the same azimuth angle, they might overlap with our existing storm. So let's say we set our maximum unambiguous range to not go out far enough to capture the storm. This storm will undergo what we call range folding or aliasing, and it will appear closer to the radar than it actually is. So in this case, we would need to increase or we would need to reduce our PRF, or how quickly we transmit pulses, in order to be able to see the storm that's farther away. And this could be problematic. Let's say we actually have a storm here and there's another storm located farther. In that case, you'd have the storm's echoes being overlaid from this far storm with this close storm. So you get contaminated data. And finally, maximum ambiguous velocity is important because you want to be able to measure the full range of velocities. And if you aren't able to do this, then you have what's called velocity aliasing. So you can see here, we have negative velocities, and then all of a sudden they become positive. So that's not physically realistic. So that's just simply an artifact of what the radar is measuring in this aliasing effect. So there are ways to correct this, but in general, you don't want to have to do a lot of this type of velocity correction if you can avoid it. So in general, we may not be able to find a PRF or PRT that perfectly addresses all of these things. So you try to find the best combination possible, maybe perhaps through some experimentation and experience. So finally, I'll close by talking about what we look for when we go out in the field for radar sites. So we'd like to have a clear view, so very few trees, buildings, hills, and other obstacles. So here's an example of a good site where there's very few obstacles that's impeding the radar from scanning this thunderstorm. If there are lots of trees and hills, then we usually try to find an open sector in the area of interest. So if there were trees not in front of the thunderstorm, but they're behind off on the other direction from the thunderstorm, we wouldn't care about those trees necessarily in this case if we're just scanning this thunderstorm. We need the radar site to be level. So this is important for the interpretation of our data. If the radar is not level, we can't assume the data are all at a constant height and elevation, or elevation will actually be varying as we scan around, which would be really hard to compensate for. So if you have a really extreme slope, it could, while we do have hydraulic leveling, we may not be able to actually level the truck. And finally, radar sites should be off the road as much as possible, or at least in a very low traffic area. So we typically find a pull off like this and pull off as far as we can onto the pull off, and also try to make the radar and the crew as highly visible as possible. So general safety practices, crew safety is most important during a field experiment. All participants are expected to report hazards immediately to the person in charge. Light weather related hazards are an important consideration, lightning and flooding especially. Lightning can happen anywhere, anytime when you're around thunderstorms, so that's especially crucial. Hail, severe weather, and severe winds and tornadoes also are sometimes considerations. And one of the most important things too, field experiments involve a lot of driving. So that's probably the most dangerous activity in the field project itself. And the driver always has to be very attentive. So in summary, the weather radars give you a wide range of unique scanning modes to get information about the atmosphere. Different phenomena require selection of the temporal and spatial resolution, vertical sampling, and scan depth. And you have to very carefully choose the different radar parameters to kind of optimize this range velocity performance. And this can often be challenging because a lot of times we want to see many different phenomena simultaneously. So we might want to get a lot of detail about the sea breeze and also the thunderstorm that's forming, or that is formed off the sea breeze. So, and that is the end of my presentation. So I will turn it over to Pierre. And then maybe after that, we can take any questions if there's time.
Okay. Okay.
Yeah, 20
Thank
minutes.
you. Thank you, David. So I will share my screen quickly. All right. Can you see it?
Got it.
Okay, perfect. So I will not share my full screen because I want to toggle back and forth with the web page. So I will go quickly with some quick introduction. So my presentation focuses on radar applications, and I want to give examples with radar products that are used operationally. So I acknowledge David and Barry for their contributions. When it comes to radar, we have a unique tool here to sense weather and / precipitation, which provides unique 3D view at a regional scale and at comparatively very high resolution compared to satellite sensors, for example. Also, all these sensors are consistent through the hydrometeors that they sample. They are different by observation time, location, resolution, and algorithm. Weather radars provide uniquely 3D/4D view of weather at fine resolution and over regions. I will really go over quickly this one because David did a very good job at describing how a radar samples the atmosphere. So you can see here tiny at the bottom the radar, and it sends waves that will interact with clouds and hydrometeors that typically are more in the ice phase aloft and in the liquid phase near the ground. The beam the beam broadens as we go farther away from the radar, and it typically takes some time for radars, especially operational radars, to complete a full volume scan. Also, you can notice here the cone of silence that David mentioned. So when it comes to applications, you need to account for some specific limitations. And also, importantly, you need to account for the context and the need, and all start from there. And I want to give that very quick example that happened to us here in Norman a few years ago. An emergency manager called Jerry Dennis from Southern Colorado came to us and basically asked for a weather radar. And he was concerned about burn scars near his city, who are areas prone to flash floods and debris flows. So he wanted a mobile radar similar to Raxpol to be deployed nearby because he wanted to be able to warn the population whenever some rainfall would come their way and maybe rain over this burn scar and generate flash floods. It turns out that in this region, the operational radar coverage is not good. And what we have here is that the typically mountains block the radar beam propagation in the atmosphere, and operational radars are blind behind the mountain. So what Jerry wanted is a radar located in this area to monitor what's going on near the surface. So we had issues of beam overshooting, below beam effects, and sometimes mixed phase sampling. So on the left here, at the bottom left, you can see the county's delimitation, the mineral county in the southern Colorado. In blue, you have the delineation of the burn scars. And for the same event, this is what is seen by the operational radars, basically not much going on. But with the mobile radar, we were able to monitor precipitation near the surface and detect activities that could be potentially threatening for the population. So this is a kind of context that you need to account for when you design a radar application. Not only we wanted better radar coverage, but also a need for real-time information to the Weather Forecast Office. And that's the Weather Forecast Office of Pueblo when we deploy the radar. And on this big screen on top here, you can see the radar images that we were able to provide them in real time. So when it comes to application, because of some limitations associated with weather radars that David presented, it is advantageous to use multiple radars nearby that can complement each other. And this is the very basis of an operational system that I'm going to quickly present, the multi-radar, multi-sensor. Here on the top left, you can see the radar reflectivity sampled by a single radar at a given elevation angle. And if you compare the precipitation estimates that you derive from these radar observations, the comparisons are depicted here. The white colors mean that we have almost no bias, and red colors mean that we have an increasing underestimation from the radar. And you can really see a pattern, really depending on the range to the radar, which indicates that at larger distances, we have increasing underestimation because the radar beam samples higher altitudes in the atmosphere. So a single radar will have this typical kind of bias. But if we take advantage of the nearby radars and perform some compositing, here we can cover evenly broader areas. And here the comparison with gauges doesn't display anymore this range-dependent kind of bias. So the multi-radar multi-sensor system does exactly that. It combines sensors, especially radars, over the entire US and provides update cycles of 2 minutes at a spatial resolution of 0.01 degree. The idea is to combine also these radars with information coming from gauges when it comes to estimate precipitation, as well as model hourly analysis. Objective is to depict the 3D storm structure. And this system has been transferred to operations at NCEP some time ago, as well as is used by the FAA for aviation purposes. In the future, because the temporal resolution is very important to study weather, the future technology like phased array is expected to provide better vertical resolution to the system. So just as an example here, you can see on top right the location of the various radars in the network in white. In red, the tiny red dots correspond to the gauges. And at the bottom, you can see precipitation systems that spans the several latitudes in the US. And the entirety of this system couldn't be sampled with a single radar. You can only do that with a radar network. So let's go over what we can do with this kind of tool. We have typically 3 different type of applications. Some of them overlap. Severe weather, aviation, and hydrometeorology applications. So we'll start with what could need a forecaster and products that are used to monitor weather, so reflectivity products. So I show here a web page that all of you can attend, all of you can go to if you want. You can see the address here. You can type MRMS space viewer on Google, and that should be one of the first entries. So first, it covers the entire US plus some external areas like Alaska or the Caribbean. And it provides in real time, this is the current situation over the US of precipitation as seen by the radar network. You can also loop over these different products. So I guess you want to go to Florida, right? So let's zoom a bit and see what's going on. So at this time, we have some, systems, some precipitation, moving forward to, and that will reach Gainesville, I guess, in less than 1 hour. That's product that we see here is a composite reflectivity. So it gathers reflectivity data that are sampled by the various radars nearby. So if we wanted to see the radars nearby, I can do that with overlays WSR ADD radars. So you can see them now. Yeah, those the observations taken by those various radars are used to generate this composite reflectivity. If we were to use only one radar, we couldn't cover such large area. So the composite reflectivity is used by forecasters to interrogate radar observations in regions of meteorological significance. Well, it turns out that something is happening in Florida right now, but if we go, I don't know, to Kansas, nothing much is happening at this time. So a forecaster can decide to focus on, Gainesville and to issue a warning. So from there, you can guess precipitation intensity near the ground. I will come back to that later. And you can also, perform some storm triage over large areas. You can identify area where you have higher reflectivities, like above 50 dBz, which probably indicate very high rain rates and or the presence of hail. So because a radar provides a 3D view of the storm system, you can get some information about the vertical development of storms. And for that, we can look at the ecotops, for example. And we have some, remember here, we had some high intensity. Yeah, you can see that there is some very significant vertical development with values reaching 14 to, 15 kilometers above the ground, above the sea level here, as a way. So that that is indicative of very strong activity that might be of interest for a forecaster for applications. You can interrogate the altitude at which the radar sampled 30 dBz, 50 dBz, and 60 dBz. What does it tell you? Well, it tells you, it indicates areas of turbulence near storm tops, but also storm severity. For example, overshooting tops, maybe the one that we have here at 18 dBz that reaches very high altitudes, might be an overshooting one. Personally, at this time, I would suspect rather a radar artifact. And by monitoring the system as it evolves in time, thanks to the temporal resolution of the system, you can monitor also updraft pulses that are indicators of the life cycle of the precipitation system. You have also thickness products, like the sampling of very high reflectivity above the isotherm 0 degrees C can indicate the presence of hail or strong updrafts. So for example, it has here a direct application for aviation. As on this plot, can you see it correctly? Because I'm not sure. Can you see the lines?
Can't leave it there. We got them.
Okay, got it. Great. So you can see here how, so that product that is shown is the ecotop height at 18 dBz. And you can see that there is a cell here that is generating ecotop heights at 18 dBz that are at high altitude, like 14 or maybe 14 kilometers above the ground. And that is right on an airline track. So what is in order for this track here is to reroute the plane in order to avoid this area that could be very dangerous. So you can follow in real time what's going on with these storms, and adapt the flights. Hail products are something that received a specific attention and generated the development of a number of products. You can see that hail here. So we have a severe hail index. Well, the index is pretty low at this time over Florida. We have almost no probability of severe hail, and the maximum expected hail size, no, it's pretty small. I don't know if you've seen oftentimes hail in Gainesville, but you can monitor that with the system. Here, the hail swath is provides you with the maximum probability severe hail index value. Sorry, the maximum hail size that has been estimated for the last 30 minutes. If you apply the same for the last hour, you can get a broader area. But it gives you some indication that there is some hail activity in the region.
Here, you got 2 minutes.
Okay, thank you. Hail product. We have also from radars, you can get velocity-based, rotation-based products. I need rotation here. Well, at the low levels, at this time, nothing much is going. Very low values, very low rotation values that are indicative. And you can get also products like tracks that tell you about a bit about the life cycle life cycle of these storms that are generating azimuthal shear. And this is a product that is especially useful for tornadoes. So I don't expect that to find that today over Florida. So I will pass quickly on the lightning products, and I will spend my last minutes on showing a bit about estimation of precipitation at the surface, which uses inputs from radars, gauges, and also the ARRC model. So for that, you get here the precipitation rates estimated at the surface in inch per hour, red colors corresponding to higher precipitation rates, and in blue, lower precipitation rates. And you can expect some activities this afternoon. At 15 minutes accumulation, 6-hour accumulations are also, we can also display them. Something that could be interesting also is the monitoring of precipitation types. So you can see on the right the different types: convective in red, warm stratiform in blue, and in purple you have hail cores that are detected by the MRMS system. So this enables to target areas of potential interest within the storm when you sample it with Raxpol. I will from there you can run an hydrologic model, force it with those precipitation rates in order to estimate whether or not there is occurrence of flash floods. So I will stop the image looping, but you can see here the streams, and an hydrologic model converts the precipitation rates into springfall values. So I will stop here and we'll take any questions.